Good morning, students. I am Dr. Hariprasad Upara, working as assistant professor in chemical engineering department. So, in the fifth semester, I am going to handle this elective course. So, that is numerical techniques in chemical engineering. And the prerequisites required for this course are heat transfer, chemical reaction engineering, mass and momentum transfer. Uh, so, this is a 3 credit course and it is covered with 5 units. So usually if I want to discuss brief about this course, so in any chemical engineering system, we are performing some experiments and finally we are interpreting those results. So these results, that interpretation, it can be done either by qualitatively or quantitatively by introducing some mathematical principles. So in order to investigate this general behavior of the system, so which one is affecting on what parameter is affecting, that is what we are going to study by applying some mathematical principles. That is what we are doing in the first step. So whereas in the second step, so we should collect some relevant information, so in the form of conservation of laws and rate equations. You might have already studied about law of conservation of mass, energy, momentum. So the same thing that you are going to study in this numerical techniques in chemical engineering. So in the first unit, so you are going to apply law of conservation of mass and energy balances. So what the law of conservation of energies in chemical engineering systems are basically involved with material balances and energy balances. So and also the rate equations should also helpful for developing the relationship between the fluid flow and the driving forces. So when we develop these when we finally when we write these law of conservation of mass and energy equations, that finally it will end up with the mathematical equations. So those mathematical equations that we are discussing in unit 1. So for a particular system, we are like, for example, in this unit we are considering single stage extraction process, mixing process. So for these two systems we are writing the material balance and we are trying to obtain one mathematical equation. So how to solve that mathematical equation, that is the secondary step. So first we should able to write the law of conservation of mass and energy balances. That is what we are going to study in the unit 1. So whereas in unit 2, ultimately when we have this mathematical equations, so it can be in the form of an algebraic equation, or it can be in the form of differential equation, or it can be in the form of a finite differential equations. So finite differences, so ultimately we need to solve these equations. When we solve these equations, we should know the numerical techniques. So by applying any one of the numerical technique, we are solving these mathematical equations in the form of algebraic differential equations, and we'll end up with the result which it will use the significance of that physical significance of the system by solving the equations. So like in the unit 1, for example, like liquid mixing systems. So for this, suppose there is a liquid mixing system is there, in which there is an inflow of substances and outflow of the substances are there. So for this, first we should write the law of conservation of mass. What is the inflow and what is the outflow? Based on that, we will get one algebraic equation. So for the same system, if we have the energy, like for example some reaction is taking place in that liquid mixing system, some exothermic reaction is happening, in that case we need to write the energy balance equation. So that is also end up with some mathematical equations. So by simultaneously solving these mathematical equations, we will get the how the independent variables are affecting on the dependent variables, that can be examined basically in this unit 1 and unit 2. So in unit 2 we are writing some mathematical formulations for the complex problems, like gas liquid contact, and also some series parallel reactions, as we have studied in chemical reaction engineering also. Like for example, some reactant A is getting reacted and giving rise to the product B, and again B is getting giving rise to the product C with some rate constant K1 and K2. So for this we are writing the equations, mathematical equations. We are applying continuity equation and mass balance equations we are writing, and it will end up with the ordinary differential equations. So these ordinary differential equations, if we can solve, then we can came to know how the concentration profiles are varying with respect to time. So that can be examined, and ultimately we need some numerical technique for solving this kind of series parallel reactions. That is what we are going to study in unit 2. Similarly in the unit 3, it is the application of non-linear algebraic equations. So we need to formulate the non-linear algebraic equations, like one of our chemical engineering application is pressure drop in a pipe. So as we have studied about Kojni-Karman equation. So for that, how to solve the equation by using the numerical technique. So in this we are using Newton-Raphson method to solve such kind of non-linear algebraic equations. Similarly, whereas in the same unit there is an application of the initial value problems. Like for example, we are taking a series of stirrer tanks. So for this series of stirrer tanks, we are writing the law of conservation of mass and energy balances, and based on that we are solving the equations using Runge-Kutta method. And whereas another kind of application is by using final value problems. So for this we are taking one-dimensional steady state heat conduction problems, and based on that we are using discretization technique, how the heat getting transferred from one end to another end, and we are applying some numerical method like discretization finite difference method we are applying, and we are estimating what is the temperature at each node. That can be estimated by using final value problem. That is the application for the final value problems. Similarly, in unit 4, it is dealt with about partial differential equations. So in this partial differential equations, majorly we are dealing with some chemical engineering applications like Fick's law of diffusion and heat conduction in the rectangular coordinates, and also heat conduction equation, how to solve this kind of heat equations by using finite difference method. Means we are applying finite difference method to solve this kind of chemical engineering applications. Similarly, even extraction problem and continuous stirrer tank reactor problems will also be considered for solving these kind of applications by using finite difference method. And finally, in the 5th unit, it is mainly deal with applications of the Laplace transforms. So this Laplace transform we are going to study in the process control also. Same thing here also, by taking some systems of our chemical engineering systems like level controller, single tank systems, mixing systems, or CSTR with the first order reactions, or interacting and non-interacting systems. For this we are writing law of conservation of mass, law of conservation of momentum. So after writing this, it will end up with some mathematical equation, those mathematical equations that we are solving by using these numerical techniques. So basically I am going to follow these textbooks. One is Meckley-Sherwood, that is applied mathematics in chemical engineering, and one more is Jensen and Jeffrey, that is mathematical methods in chemical engineering. So most of the syllabus was covered in these two textbooks, and along with that you can refer one more reference book, that is applications of mathematical model to process development. So this course it is an application to the chemical engineering system. So whatever we deal with, whatever we study in fluid mechanics, heat transfer, mass transfer, those examples we are considering, and we are applying numerical methods to solve those kind of problems. So I hope this subject is going to be very interesting, and it can be helpful for solving the chemical engineering systems. So thank you so much.